In this lecture, we're going to introduce the idea of bounds and certificates. And by certificate, we mean a certificate of optimality. We'll define that later. For now, let's consider a particular problem. Here we have some integer program, and the optimal solution to this linear program or integer program is going to be z star. But let's suppose that we solve this integer program, and z is the value of our solution. We'd like to know, is the value of our solution equal to the value of the optimal solution? And if it's not equal to the optimal solution, how big is the difference? So how big is the absolute value of z minus z star? To answer these questions, we're going to introduce bounds. And to answer this question of optimality, we're going to introduce the idea of a certificate. The idea of a bound is quite simple. We have some optimal value to our integer program, z star. And an upper bound is going to be anything that we can say is provably better than z star, that is, has a higher optimal or objective value. In this case, we have a sequence of bounds, z1 bar through zt bar, and this is a decreasing sequence of bounds. Lower bounds are similar. We have z1 lower bar to zt lower bar, all of which are less than our optimal solution z star. And again, this is an increasing sequence. We'll work more with bounds in the coming lectures. A certificate is the key idea we'd like to get across here. And a certificate is something that's going to tell us that our solution, the one we have in hand, is going to be an optimal solution. So specifically, if we have some solution, little z, and it's feasible, then if we have another value, another z hat, it's going to be a certificate of z's optimality if two conditions hold. First, this z bar is going to be an upper bound on our optimal solution, z star. And also, the value of our solution, our feasible solution, z, is equal to z hat. We can see why this is going to be a certificate of optimality. Although we haven't said it here that z hat implies z is optimal, we can sort of just derive a simple proof of it. So let's suppose that our z is feasible. And immediately, because z is feasible, we get a conclusion that z is going to be less than or equal to z star. Because z is feasible and we're looking at a maximization problem, the optimal solution has to be at least as big as our feasible solution. Now if we add in this idea of a certificate, this z hat, and it's going to satisfy the conditions of a certificate, then we know that z is going to be greater than or equal to z star. We just use these two inequalities. First, z is equal to our certificate value, and we know that our certificate value can be proven to be above the optimal objective value. Together, these two things imply that z is equal to z star. And what's doing the heavy lifting here is the z hat, our certificate. This is what's proving that z is equal to z star. In this way, the certificate is a certificate of optimality. The idea of a certificate is really important when we're proving optimality. In order for a solution to be optimal, we usually have a corresponding certificate that it's optimal. But when we're running an algorithm that actually solves integer programs, we're usually going to have to settle for a solution that's just good enough, that has some bound. And in this way, we're going to have some stopping criteria for our algorithm. That is, once we get a solution that's good enough, our algorithm can stop and we can output this solution. The main workhorse behind the stopping criteria are going to be these upper and lower bounds. And that's why we have an increasing sequence of lower bounds and a decreasing sequence of upper bounds. Let's see exactly how this is going to work. Let's suppose that we have some solution, z, that's feasible. So z is going to be some feasible solution. And we can say that this is going to be some feasible solution that our algorithm is going to generate. We're going to know a few things about z. Usually, when we develop an algorithm, we're going to have corresponding lower and upper bounds. So let's suppose we have a lower bound for z, zt lower bar, and an upper bound for t, zt upper bar. We also know that our optimal solution, z star, is going to be at least z lower bar t, let's move the t, and is going to be less than z upper bar t. This is from the definition of our bounds. Z star is going to be sandwiched between these bounds. And now let's further suppose that the distance between our bounds, Z upper bar t, minus Z lower bar t, is less than or equal to some epsilon. So this is a setup of the internal workings of an algorithm. We have some feasible solution, Z. We know that Z is sandwiched between some bounds. And we know that our bounds are within some factor of each other, within some epsilon. All of these things end up implying that the distance between our solution, our algorithm solution, and Z star is less than or equal to epsilon. And we could go through some algebraic proof, but it's not very useful. Really what we just need is the intuitions. We have some lower bound, Z lower bound t, and some upper bound, Z upper bound t. And we know that the distance between these things is epsilon. We also know that our algorithm solution Z is within this region. And we also know that the optimal solution is within this region. So the difference between our optimal solution and our solution has to be at most epsilon. This is going to be fundamental when we get to algorithms. For now, and for the rest of this lecture, we're going to consider this only in terms of the bounds and what a bound is going to tell us about the quality of our solution. So now that we know what bounds are going to be used for, in particular, bounds are going to be used for certificates of optimality and for stopping criteria of algorithms, let's figure out how we're going to actually get these bounds. First, let's talk about lower bounds. Lower bounds are typically called primal bounds. And really, we only have one technique to get lower bounds. Any feasible solution to our program is going to be a lower bound on the optimal solution. There's really no other technique. Unfortunately, because of this feasibility issue, this might actually be hard to find a lower bound to our program. And sometimes finding a lower bound can be as hard as solving the program itself. This will be a point to come in the future. And when we're looking for lower bounds, these primal bounds, they are never going to provide a certificate of optimality. On the other hand, upper bounds, which are usually called dual bounds, do provide certificates of optimality. And because of their role in showing that a solution is going to be optimal, we're going to focus on them first. So for the rest of this lecture, we're going to develop techniques to find upper bounds and also evaluate the quality of these upper bounds.